Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. Today I will teach unit process. This is the lecture 8 and we have discussed the corrosion and what is the effect of the catalyst and the coating lining on the surfaces for manufacturing of the equipments during the equipments. So in the previous lecture we have discussed various topics so factor controlling the alkylations. There are so many factors which are affecting the alkylations process and the effect of alkylations, uh, and then technical alkylations. In technical alkylations we have manufacturing this alkyl aryl detergents. We have discussed about the flow sheets of how we can prepare the detergents by using the different components, different reactants. Okay, so in between, if you will see this image, this is a initially wall and before, and this is after. So here is a one layer of is there, and after bursting, when the pressure increase, it is break. And this is a distillation column for the separating or the purify or substance. We have required this distillation column, and this is the molar coating we can do on a surface of um, equipments, and catalyst also we have used. And this the application of this alkylation can happens in petroleum industry. So this thing we have studied. Okay, so so now today we will and the another is alkylate for the petroleum industries. This thing we have also discussed in the previous lecture. And this is the main reaction which is used for the alkyl aryl detergent. This reaction, if you will see here, so the main reactant are benzene and dodecene, which is when in the presence of aluminum chloride at 150 degree Fahrenheit, so they will produce dodecyl benzene. Okay, and after producing this dodecyl benzene, we directly send to the sulfonator chamber, and then neutralizer. In the sulfonator, the sulfuric acid, they react with sulfuric acid, and then they neutralize with sodium hydroxide, and then finally you will in the dry you will send, and then they will get its powder form, and you will collect. That is called the detergent. So this is a way you can produce the detergent. Okay, so now you will see this is a flow sheet for alkyl aryl sulfonates, and this is a storage tank, and here this is a benzene and dodecene in this. Okay, and when you will directly send to this crude oil in this benzene fractionator. Actually, this is the previous one we have discussed about this how we can create this detergent. So this we have used the three type of fractionator, and the first one is benzene fractionator, and the another one is the intermediate fractionator, and then finally is the dodecyl benzene fractionator. So from the bottom we generally collect all the things, and then we will send directly to the intermediate, and then dodecyl benzene fractionator. But in the lower part of the bottom we do not collect here, because it is a heavy alkyl aryl hydrocarbons which we have not required. So only the dodecyl benzene fractionator we have required, and then we directly send to the in the storage tank, where and then treated with the sulfonator section with the sulfuric acid, and then the whatever the extra sulfuric acid is available in your system, you can remove easily in a spent settler, and then we directly treat it with the sodium hydroxide here in this neutralizer, and then you will sodium dodecyl benzene sulfonate you will get it, and then this by in a dryer you will collect it dry detergent packing, and this is you can dry by the combustion gases. So this is the simple flow sheet for the alkyl aryl sulfonates, which is a type of detergent we generally prepare for many purpose. Detergent can use for the household purpose. Okay. Now we will discuss what we will discuss today. The first one is the technical alkylation. So two parts we have already discussed for alkyl aryl this one alkyl aryl sulfonates we have prepared. Now we use the thermal alkylation and the this HF alkylation we will read, and sulfuric acid alkylation. So these three we will read today in technical alkylation. So in a thermal alkylation has ceased to be commercial process. It is a commercial process. Neohexanes, the main product of the thermal process, has a research octane number of 104.8 with 3 ml tetraethyl lead per gallon as determined by Phillips Petroleum Company, 103.8 on new API scale, while the corresponding number of diisopropyl with 6 to 6.8 ml TEL, which is tetraethyl lead, is 118.7 and 120 new API scale. This diisopropyl is obtained by catalytic alkylation. Okay. For this reason, and because the thermal process operated under the extreme conditions of 5000 psi pressure and the 950 Fahrenheit temperature, it is very doubtful if the operation will be resumed. Actually, for this extreme condition, so it is very difficult to sustain a equipment. So now another is hydrogen fluoride alkylation. The alkylation reaction of olefins with isoparaffin catalyzed by anhydrous liquid hydrofluoric acid are carried out on a large scale commercially. Okay. The highest quality of alkylate is produced by the reaction of isobutylene with isobutane to form mainly isooctane, which is 2,2,4 trimethyl pentane. The reaction procedure, a number of other products including those having more or less than 8 carbon atoms, that we'll see in the table 14.4, that will be in next slide. You will see, to ensure useful reaction rates, it is necessary to provide agitations, because the hydrocarbons are only slightly soluble in the catalyst liquid hydrogen fluoride. So you will see here, so this is a 14.4 table which describes some hydrocarbons formed in HF hydrogen fluoride alkylation. So this catalyst generally used. So hydrocarbon products, so this alkylation of isobutane with propylene, when the 2,4 dimethyl pentane, which is 10 to 15, percent approximate total percent in total alkylate, and 2,3 dimethyl pentane, which is 40 to 50%. So other hydrocarbons like pentanes, hexanes, and 2 to 4 trimethyl pentanes, and other isooctanes, isononanes, and isodecane and isodecane, alkylation of isobutane with butylene, 2 to 4 trimethyl pentane, which is 35 to 40%, 2,3,4 trimethyl pentane, which is 20 to 30%, and 2,3,3 trimethyl pentane. Okay, so other hydrocarbons, which is isopentane, 2,3 dimethyl butane, 2,4 dimethyl pentane, 2,3 dimethyl pentane, dimethyl hexane, isononanes, including 2,3 5 trimethyl hexane, isodecane, isoundecanes. So these are the some few percentage available during this HF alkylation. Okay, so this is a data of Phillips Petroleum Company. Okay, so the other olefins react similarly, but isobutane is the sole isoparaffin used. The best available are for the alkylation of isobutane with the mixture of 80% 2-butene and 20% 1-butene. The effect of increasing the isobutane olefin ratio in the feedstock is to improve the yield of acceptable alkylates and to improve the octane number of that alkylate. So the former effect is great until the ratio of 5 or 6:1 is reached, after which it is slight. A change of ratio from 4 to 14 improve the octane number about 4 units. The effect of acid is to hydrocarbon ratio is not critical, but a ratio 1:1 seems to be favorable, convenient and economical. Okay, so the temperature commonly obtained with the cooling water are satisfactory for this reaction. A high temperature lower the quality of alkylates, but too high or too low a temperature results in excess organic fluoride formation. A temperature of 27 degrees centigrade results in alkylates about 1 octane unit better than that obtained at 46 degrees centigrade. So the contact time of over 5 minutes do not affect the yield, and the octane number is at a slight maximum at contact time of 15 minutes. So an acid strength of 87.5% gives the maximum octane alkylate, but the balance of the acid phases should be organic. If water content of less than 2% is not very harmful, but octane are replaced by heavier and lower hydrocarbon as the water content build up. And the fluorine content and the olefin content in the alkylate build up in the presence of excess water. Okay. So the alkylation reaction with hydrogen fluoride as a catalyst is complete in one cycle when it is run under the condition indicated above by dispensing with bauxite defluorization tower, and these results a consumption of 0.2 pound, which is LB, of hydrogen fluoride per barrel of alkylate. So this is a consumption of hydrogen fluoride which is used for this alkylate reactions, and the hydrogen fluoride which is no longer suitable for alkylation is regenerated by two-step distillation procedure. So this is a one difficulty which is for if you want to reuse this hydrogen fluoride, so that is very critical to get for reusing. So we have required a two-step distillation for regeneration of our catalyst. In the first distillation, hydrogen fluoride and water are flushed away from heavy acid soluble oils, which are next reboiled to split out combined hydrogen fluoride. The overhead from this operation is rectified to produce this sustainable pure hydrogen fluoride overhead, and a maximum boiling water hydrogen fluoride azeotrope containing about 35% hydrogen fluoride as bottom product, which is discarded. So this thing we generally get. So for the typically operation condition and yields are given in this 14.7 table. So this is a 14.7 table which is the provided the typical operation of paraffin olefin alkylation process, and these are the operating condition. If you will see, this have the three operating condition are given for the thermal alkylation and the HF alkylation and aluminum chloride complex alkylation. So but here we will discuss only the HF alkylation. The thermal alkylation condition we can also see. So the molar isobutane olefin ratio. So in the HF alkylation it is required 4 to 8:1, and the contact time is 10 to 20 minutes. And for this thermal alkylation it is very less, which is 4 to 4.5 minutes. But the reaction temperature is 930. The reaction temperature is very high, and but in the case of HF alkylation it is required very less, which is 70 to 115 degrees C. Degree Fahrenheit, and but the reaction pressure which is very high in case of thermal alkylation, which is 5000 psi, but in case of HF alkylation which is 125 to 175, but the catalyst in the reactor volume percent is none. We have not required any catalyst, but in HF require 45 to 60%, and for acid strength of percent HF it is 85 to 95%, and Al2 content we have not required for this system. And the charge and yield, which is hydrocarbon reacted ethyl in isobutane and butylenes, amylenes and isobutanes. The total alkylate yield pound per pound olefin reacted 1.3 to 1.4, and isobutane consumes Lb which is 0.8 to 95. So this thing is there. These are the some conditions for HF alkylation and thermal alkylations, but aluminum chloride complex alkylation we will read in further slides. So then we will discuss in this table comparison with this. Now we will discuss about the sulfuric acid alkylation. So despite some advantages such as acid recovery expense and the refrigeration to minimize oxidation, about 4/5 of the alkylates produced for motor fuels is based on sulfuric acid as a catalyst. As with the HF alkylation, isobutane is alkylated with olefins other than the ethylene, and a flow diagram for such a process which is shown in figure 14.5. The flow sheet we will discuss later. First, the alkylation is exothermic. This reaction is exothermic, and means must be provided to control the temperature and to secure the good contact with the reactant and the catalyst. This is done by having the sulfuric acid saturated with the isobutane, and by feeding the olefins into the system in such a manner to provide the isobutane in excess. Okay, so this is the flow sheet for the sulfuric acid alkylation for petroleum alkylate. Okay, so if you will see here, so this is auto refrigeration system, and this is a storage tank where the olefins are we will feed, and this is a cascade alkylator system, which is fresh acid we will directly send, and some recycle we can also send. And then what we will do, we directly send to this depropanizer. This is a depropanizer column. Inside this we will send, if you will see here, so this is the arrow is going here, so the sulfuric acid and olefins we directly send in here, and we will mix. From the top side we will directly get it the propane, and from the bottom, from the residue, you can say in the bottom generally we say the residue, so we will directly send to this effluent treater, and then directly send to this isobutane tower. So the first one is a depropanizer, and the second tower is a isobutane tower. So here, so this isobutane we will directly treat with isobutane, and then from the bottom part we will send to the debutanizer. Okay, and then again we will butane. In the previous one isobutane we will send, now here we will butane, we will some part we send, and we will collect butane from the top, and then again we will send to the rerun tower. Okay, so here we are using the 4 towers. The first one is depropanizer, the second one is isobutane tower, the third one is debutanizer, and the fourth one is rerun tower. And then you will get it in the from the bottom is heavy alkylates, and from the top you will get aviation alkylate. Okay, so this is the thing we will get from this. So the 4th tower we have required for purify our products. Okay, so this procedure and keeping the temperature down minimize any polymerization of the olefin used. So temperature we have to reduce, because any other polymerization cannot happen. So as practically employed an emulsion of the acid, and the isobutane is circulated in large volume past the point of the olefin injection, while the alkylation reactors can employ indirect heat exchanger, the one depicted in figure 14.5 and detailed in figure 14.6 that will show later, employ auto refrigeration by. So this is a auto refrigeration system. This is a 14.6 figure you will see here, which this part we have already shown in the figure 14.5, where we are using this one because we are mixing this sulfuric acid, which is a very exothermic reaction generally happens, so we have to cool the system. So this is here for this is a recycle acid we directly send, or from the top we will charge isobutane, recycle and refrigerate. So these are the different columns different stirring system, and from here you will spend recycled acid, and this is the reactor effluent. From this side you will get it, and here it is a two compressor. We are using the compressor, and from the bottom the olefin we will feed from the bottom. Okay, so these are the things. This system is called Killo's cascade alkylator. Okay, so this is the thing, or this is the auto refrigeration system. Okay, the evaporation outside condensation and returns of isobutane or other low boiler to maintain the temperature at 35 to 45 Fahrenheit. Isobutane is charged and is also returned from the deisobutanizer tower. The olefin are injected in a small amount in each of the 5 successive zones of the reactor. So you have seen there is a 5 successive zones in the reactor, thus maintaining a high ratio of isobutane olefins in the reaction zone with low isobutane concentration in the effluent. The right hand or settling zone of this cascade reactor, as shown in figure 14.c, this serves to separate isobutane vapor going to refrigeration system and from the spent and recycled acid and the effluent. The effluent is fractionated in the series of 4 towers. Actually, if you will see in the 14.5 figure, so there are 4 towers. Okay, and we will that effluent we will send there. So typical results are summarized in table 14.5. that 14.5 we have already discussed. The higher the isobutane and concentration, isobutane to olefin ratio, acid to olefin ratio, and the acid strength, and lower the reaction temperature. The higher the octane rating of the 338 Fahrenheit and point materials, and the lower the acid consumptions and the quantity of heavy polymer forms. So for the higher octane rating, we have required, sorry for this, for the higher octane number, so we have required this 338 Fahrenheit endpoint for the material and the lower acid consumptions. As the sulfuric acid is contaminated, a portion is withdrawn and replaced by fresh acid. So the effluent treater is to be remove acidic material. So this is a typical sulfuric acid alkylation yield data, and this is a table 14.5 which is we have discussed in the previous slide. If you will see here, so this is the olefin, the column 1, which is a olefin feed type, and in the second column which is the propylene, and in third column which is 40% and of 60% of this carbon percentage of this, and the butylene and pentene. So these are the 5 columns. Okay, and what is the yield for the propylene, which is 1.7 olefins, which is 1.78 bbl, and this is 1.74 for the 40% or 60%, and 1.72 for butylene, and pentene for 1.6. and when isobutane consumption, this is 1.275 and 40 it is 1.174, and for this butylene column it is 1.106, and for the pentenes it is 0.965, and the acid consumptions in 98% hydrogen sulfate per gallon, and total alkylates which is 2.5 to 0.84, and 1.5 to 0.6, and 0.84 to 0.33, and 1.0 to 0.4, and 338 Fahrenheit and endpoint alkylate quality. So you will see the octane number you will get is 80 to 92% for the propylene, and 92 to 95 is 40% or 90 60 80% 60%. So for butylene it is for 94 to 97. So for the pentene it is 90 to 93. So maximum you will get it in case of butylene, maximum octane number you will get it. Okay. So so the TEL at TEL is tetraethylene, so which is 1.03 1.5 to 1.0 103 103.5 to 105, and for the butylene case it is 104.2 to 106.3, and pentene it is 103 to 103.6, and F2 ASTM octane number which is 87 to 90%, and 90 to 93, and 92 to 94, and 90 to 92, and F3 is 117 to 122, and 124 to 127, 127 to 132 for the butylene, and this is 116 to 123. So these are the different TEL or the performance for the different, and this is for the 3 carbons performance number of 46 cc TEL, which is 129 to 142, and 141.6 to 154, 152, 162, and 136 to 148. Okay. So we have seen these are the typical sulfuric acid alkylation yield. So if you will see this Killoch cascade alkylator which we have used here, this is a auto refrigeration system. Here we are using this, and the one another thing is, so these are the 1 2 3 4 5, these are the olefins we are feeding in the 5 sections, as we have discussed in the next slide. So these are the 5 successive zones in the reactor. We are a small amount of olefins we are injected, and but and these you will get it from here. You are spent recycle acid and reactor effluents, and upper part is this compressor is there, and charge isobutane from recycle refrigeration. So here. Okay, so now you will see here for the auto refrigeration system. Okay, actually this is a cascade alkylator, I'm sorry. So this is a refrigeration system, and this is a cascade alkylator, both are the different. This is a cascade alkylator. So here these are the 5 times we are olefins we are feeding, and the fresh acid or recycled acid we are sending from here, isobutane from the top. So these are the things, and these are the 4 towers 1 2 3 4, which are depropanizer, isobutane tower, debutanizer, and the last one is rerun tower. Okay. So now we will discuss about the aluminum chloride complex alkylation. So another catalyst used for the paraffin alkylation is liquid complex made from aluminum chloride in a hydrocarbon solvent. So the complex containing 50 to 62% by weight aluminum chloride and is understood to be kerosene selected for a certain impurities which enhance the catalytic effects of the aluminum chloride. So the isobutane is alkylated with a mixture of ethylene and propylene, the ratio of the lighter to the heavier olefins being about 4:1. In commercial production, 70 to 90 pound lb of alkylate is produced per pound of aluminum chloride. So under some conditions, 75 to 85% of the ethylene reacts according to the following overall reactions. So this is the reaction. So ethylene and this is isobutane. So you are getting diisopropyl, and the olefins for the alkylations are supplied from propane or and butane cracked, being available for alkylations as solution in isobutane. So recycled isobutane, olefin containing isobutane and catalyst are mixed and contacted in a mechanical stirred reactor. The catalyst is settled and hydrocarbon mixture is fractionated to remove propane and recycle isobutane, pentene and heavy hydrocarbons. So the product diisopropyl alkane is very high quality ingredient for aviation fuel. So we have seen in 14.6, so that data is given for consumption of isopropyl alkylate. As with the other alkylates, one compound makes up the major part of the product, other compounds being formed by the side reactions. So the operating conditions yield are indicated in 14.7 table. And as in other process variation of the operating conditions, feedstock causes considerable change in both yield and consumption of the product. So if you will see the 14.7, so this is the 14.7 table where the operating conditions for paraffin olefin for alkylation processes. So this is for aluminum chloride complex alkylation. You will see here for the molar isobutane olefin ratio is 3.5 to 8:1 and contact time is 20 minutes, which is higher than the other alkylation processes or catalysts. The reaction temperature is 100 to 130, which is slightly higher in case comparison to the HF alkylation, and the reaction pressure is 400, which is higher than the HF alkylation, and the catalyst in the reactor is 35 to 45%, and acid strength we have not required. Aluminum chloride content is 55 to 62% by weight, and the hydrogen carbon reacted, so the ethylene, propylene, isobutylene, and total alkylate yield is 2.6 to 2.8, and isobutyl consumed is 1.7 to 1.9. So conversion of olefin is 95 to 95 to, if you will see here it is 95 to 98%. Actually there's something I think you have not visible. Okay, and if you will see another table which is 14.5, so this is the 14.4, I think that table I have not included. So in the next lecture I will include that table. So today we have discussed about some technical alkylations, which are thermal alkylations, HF alkylation, and sulfuric alkylation, and aluminum chloride alkylation. So this thing we have read today, and we have seen the different flow sheets for the sulfuric acid alkylations, and what is the effect of different catalysts for suppose hydrogen fluoride, sulfuric acid, or aluminum chloride for manufacturing of this substance, the different substance. So these are the, and what are the operating conditions required for this, and what will be the conversion and yield, and what will be the pressure for the system. This thing we have read today in this technical alkylation process things. Okay. So in the next lecture we will discuss about the cumene, ethyl benzenes, hexyl hexosyl alkyl benzenes to the oxygen. So these are the different components. Alkyl benzene bonds to terephthalate. So these alkyl bonds to the lead and sulfurs, tetraethyl leads, which TEL, which is very important for the things. So these things we will read in the next lectures. So if you thank you very much. If you have any doubt related to this topic, so you can ask me in this email ID. My email ID is chemicalsuniraj@gmail.com, and this is my website. If you want to further some other information, you can check it here. Thank you.